We're live.
All right, everyone. This is another Wolfram Institute live stream. Oh, Carlos, I can hear some feedback. Okay, I can hear myself. Okay, okay. Actually, sorry. That was my version. I had opened up. Sorry. I had opened up Twitch to look at the chat. Anyway, okay. Yeah, excuse me. So today we're going to continue our study of sub-axiomatic foundations of mathematics. So if you followed the stream last time, Carlos set out to perform some computer experiments. So emulating some sample of Boolean expressions using SK combinators. I actually don't know which Carlos has selected. He just went out and selected some interesting candidates, and then he evaluated those SK combinators and inspected the the content of the intermediate steps in the evaluation of these Boolean expressions through the SK combinator emulation. And so, we want to see to what extent that intermediate content continues to retain or exhibit uh, combinator content that corresponds to Boolean functions, and to what extent it becomes kind of unintelligible, just kind of machine combinator content that seems to be kind of divorced or decoupled from the Boolean algebra that it's emulating. So this is quite exciting. I mean, just like the rest of the public, I've seen some images on social media, on Discord, on Twitter. So I've been really excited to actually see, Carlos, what you've been cooking up. So, let me delay us no longer. Please, if you want to share your screen and walk us through what you've done,
All right,
I look forward to it. Yeah, let's go.
let's go.
Yeah.
Let me see. Can I share like this? Can you see this?
Yes, I can. Oh, you used the dark background. Okay, that's interesting.
Yeah, I like the blackboard feel.
Yeah, I like it too. That's good.
Okay, so just a very quick summary for everyone who's rewatching or just joining us. What we're trying to do is emulate. So emulation means that we have two rewrite systems. They operate according to some rewrite rules, and what we're trying to do is encode the content of one of the rewrite systems into the other. And so the very specific example that motivates this whole search is in using SK combinators, a very old rewrite system in the history of computation, to simulate or emulate Boolean expressions and Boolean algebra. So, for example, here we have truth values that are basically encoded in the most simple expressions, K and SK, and then we find, for example, to do true and false and evaluate true and false, that basic Boolean evaluation, we find the appropriate expression for true, for and, apologies, which is this particular expression, and then we pass K and SK, which are the values for true and false, as
Hmm.
arguments in this expression, and then we just
Yep.
run the magic of combinators. So meaning we just apply these rewrite rules. You can see them very clearly. S takes 3 arguments, goes into this expression. K takes 2 arguments, goes into that expression. And so this is an example, right? So we have and of true and false. So this is the starting expression, and this graph here shows the multi-way system that arises from the possible rewrites. And so what's important about it is that we get to a single final state. So it's a confluence system in particular, and that final state corresponds to one of the two truth values. And so
False. Yes. Right.
so it's false because obviously true and false is false. So
Yep.
that's kind of what motivates us to sort of, okay, what if we could emulate the entire set of Boolean functions? So we have this list, which I believe was found by Stephen or
Yep.
collaborators, and basically this is all 16 of possible Boolean operators, meaning this is all the possible two variable functions on the Boolean values, right? Some of them are very familiar to us, like nor, implies, NAND, etc. And these are the ones that we're going to be mostly focusing on. But the others, just exist as well, and you can give them some names that are kind of natural. If anyone is wondering, because this came up in an earlier stream, the false and true, that some people were confused because they said, why is false encoded with this code, with this expression, and not just SK, right? Which is what we had at the top. The reason being that this false is just shorthand name for the constant binary function false, right? So it's a constant binary function that acts on two arguments, right? So that's the reason. Okay. Anyway, so I did a bunch of stuff. This is what all my hours of work have been sunk into. So I don't need to go into all this code here. We can if I mean there are some problems that we might need to figure out, especially if Nick joins. But let's start by visualizing. So we could in principle say, well, if we have an emulation of Boolean algebra, Nick did a wonderful function that he then implemented to fully encompass all possible trees of Boolean operators. So in principle, we could just choose one of these expressions and run with it. But obviously, one of the main questions I posed last time as a hypothesis is, all right, so if you have the basic evaluations of your operators, meaning the thing that on the emulated side just looks like one single step because it's from operator to value. Right?
Yes.
What does that look like on the emulated side? And we had seen some of those graphs, and what I have now is full functionality to probe fully what's going on in these evaluations.
Okay.
So let's first look at one aspect of evaluation, which is, well, first of all, we can see the evaluation multi-way graphs. So these are, so by the way, purple is, what is it precisely? I think it's S. Yeah, purple is S, and and green is K. The rewrite rules. So this is AND. So this is just a simple color code. White is true, black is false. You start from something. Into you have the tooltips. Everything is fine. So something very interesting that is already noticeable here is that some of these graphs look very similar. So what I did is I coded an isomorphism graph, right? So this is just shorthand for whatever each pair is a shorthand for the evaluation on those two. So this is actually shorthand for the entire graphs at the top.
Yeah, that's great. Yep.
So this just checks isomorphism between the underlying graphs. So something interesting is that AND has this kind of symmetry that I mean, this something very interesting about this is that these are different graphs. I mean, sorry, these are different rewrite systems. These are different rewrite graphs, right? Because they have different initial states and they have different final states in particular, right? They might have also different states in the middle, but they happen to be isomorphic as directed graphs, right? Oh, there's Nick. So anyway, so let me just show you what the evaluations on the logically relevant binary operators look like. And let's just have a stroll in the computational realm of this computer. So these things already look complicated, right?
Yes.
They look very similar. I mean, first glance you might think, oh, they are all isomorphic, but no, they're actually.
Are any of them isomorphic?
Yes. This what this
they're
graph
pairs
tells you.
again.
That's
same pairing. Yes. And now for OR. Okay.
Yeah.
Yeah.
Some interesting pattern there.
Yes.
Same pair.
Interesting. Okay.
We don't know. Anyway, let's get
fun.
into more interesting stuff. Because now equals becomes much more interesting.
No symmetry.
So funnily enough, the most symmetric thing in the universe, which is equals, is not symmetric in this sense.
Yeah. Yes. That's what I was thinking too. Right.
But anyway, so this you will see later. This is actually a very intriguing operator because these things look very different, right? One of the feelings I have is that having different combinator multi-way actually is kind of a signature of being more fundamental in a way. And the reason being that the final one I have in the list is NAND, because we know that we can reproduce
Yes.
all the operators with NAND, right? Anyway, so let's see a few more. So it implies this topologies, again, in pairs, isomorphic, kind of interesting.
Yeah, same isomorphism. Yeah.
Yeah.
Oh,
XOR is very interesting. XOR is very interesting because, I mean, look
is
at
there,
this
is there
behavior.
just is okay? Yeah, go on.
Yeah, this behavior is very interesting because these look very similar by pairs, but they're not exactly the same. This thing at the end has this affix, right? It has this protuberance here of like purple stuff, and otherwise it would be the same. So the isomorphism only happens between this more complicated two, right?
Yeah.
So any hope for some definite pattern is sort of being lost. I mean, this is just isomorphism between these two and not the others.
In this case, not to ask such a naive question,
Sure.
but the second and the fourth one, they have been run to completion, right?
Yes. You can
Yeah.
you can tell because there's the K here. There's the white, the big white
I
dot.
see. Okay.
Right?
Yeah. Okay.
The code is made so that you see the final state as a big white or big black.
Okay. Okay. Wow. I mean, the fact that they're so similar and then they're not actually isomorphism is weird.
Yeah. No. So these two are isomorphic, and these two are non-isomorphic. Right.
Yeah.
The clamp
Yeah,
clamp lollipop thing is isomorphic, and this other one is non-isomorphic. Which is interesting.
They really are. I mean, they really are quite close, except for the end.
Yes,
Yeah.
they are
Yeah.
very, very
Weird.
close. Yes, they're very, very close.
Yeah.
They are.
Weird.
Yeah. They
Okay.
differ in like one arrow here, but anyway. Okay, so NOR, another weird one.
Ah, symmetry broken. Weird.
Yeah,
Weird.
quite weird. So these all look similar in terms of graphs, but actually only two of them are isomorphic. I mean, this is
Yeah.
just strange.
And it's a different pair.
It's a different pair.
It doesn't. Yeah.
Now, converse is super simple, but look at this. Converse is not a multi-way system, it's just a single-way system. It's very interesting.
Yeah.
Converse,
Yeah.
Converse is relatively long. You can see the tooltip there. It's SSK, SKK. It's pretty long, still.
Yeah. So there are many opportunities. There are kind of many subpositions where you can apply the rule, but
Actually, only one all the time.
yeah. Right.
Interesting.
Well, right, because it's single way. Sorry, what I mean is, you would think there are many positions where
yeah.
you could apply the rule, but there's actually just one at each time step.
Exactly.
Okay, but then not converse
Not converse.
is more complicated,
It's much more
and
complicated.
and there's no and there are
there
no
is- there-
isomorphism. Oh,
There is,
there's one.
yeah.
Okay.
These two are isomorphic.
Oh my God,
Look,
that other one is isomorphic.
they are not. Like, why exactly? This is where I was getting a bit suspicious.
Wait, why those two look?
They look very isomorphic. I think they might be isomorphic, and I think there might be something not working with not converse. So I'm not sure if the encoding might be wrong. But the functions are fine because I checked them step by step. What might be wrong is the not converse encoding in the table, in the Boolean table, up above, right? We should check this later.
They look they look isomorphic.
They look isomorphic to me as well.
I went through all the vertices. Yeah.
Yeah. So the not converse here might be wrong. Because
Okay.
but we can check that later because I just did all the functions and made sure that the functions actually do what they should be doing. Okay, and finally NAND.
Wow.
Beautiful pattern in my opinion.
Wow. No NAND symmetry. It's universal, but there's no symmetry.
Yeah.
Wow.
Yeah. As it should be, I think. If it's going to be universal, if it had symmetry, it would be kind of containing less information. Anyway, so this is just a summary to get a glimpse on the topology, sort of overall shape of these multi-way systems, and some symmetry of the evaluations, right?
This is a good idea. We hadn't even discussed this, but this
Yeah.
is a pleasant surprise. Yeah,
Yeah,
this is a
it
good
came
thing
up to me
study.
because some of them looked very similar. I wasn't sure whether they were isomorphic, and I was checking with the graph ISO function, and some of them were. I was like, okay, this is a piece of information that we hadn't considered, but it might contain some information. Okay, so now on to the, our initial goal, which is to find
Yes.
motifs within it. So
Yes.
Nick is here, so maybe we can, after I give the general overview and the few couple surprises that I found, we can look into. So I have this function before I sort of spoil the results. I have this function. So basically, so I have a cool function. Let me just use it because I made a very convenient one. Okay, so if we are in, let's put this one, for example. So if we are in OR, I have this function that just does evaluations motif, and you can basically pass it one of the operators and which operator you want to search for. So for example, if I search for OR as a reality check, we should get a hit in the first state, right? Because we start with the first state.
Yes.
So hopefully it's going to produce, these are small, but if I make it larger, you can see the first state is red.
Okay.
It means that it matches the motif, it finds the motif within the expression of the first state, right? And nowhere else.
If there are, okay.
Right? So then I have this other function that, so let me just get rid of this. I have this other function that checks for all of them by matching in red, and it works. I mean, it seems to work fine. But then I change it to a color code. So instead of red, I assign like different color.
Oh, wow. Yeah, okay.
I mean, and this for some reason doesn't work properly. Like some of the vertices that get highlighted by red, when I use this multicolored one, don't get highlighted, and others get highlighted in other colors. Something weird happens. So we can look into this later, but I can just show you the basic red version that already illustrates the results that I wanted to communicate. So, okay, so we began with AND, which was very small, and it's just a reality check. Then we had OR, which nothing happens. There's no red inside. But then equal, look at this.
Okay. So you're searching for equality.
No. I'm searching for all the Boolean operators.
Oh, for all of them. Oh, you're searching for all of them.
And there's a lot of them.
Yeah. Now wait, does this include first and last?
No, it does not.
Okay. Wow. Funky.
This is very crazy to me. I don't know how to think about it. It's like, so anyway, so equal looks very interesting. Especially the beginning. I mean, this is kind of curious. Like the beginning is, I think, identical in all four cases. Might be, which that's why I'm kind of not that surprised, because if you find it in one part of the expression and you just rewrite another part of the expression, you're gonna get a lot of hits down the line, right?
Yes.
So, but anyway, there's an interesting one. Okay, so implies no hits inside. Okay.
Yeah.
XOR, some hits inside.
Yeah.
Like, look at this.
I mean, almost all of it.
Until
the end.
Yeah, except for the big cluster here.
Oh yeah. No.
And
for the first and the third.
Then
Oh, but yeah, for these two. Yeah. Wow.
It's very strange.
This is really interesting. I mean, I was expecting most of them to be like implies, where, at the entrance you're greeted by some Boolean expression, and then quickly you're just in machine land. But it's not the case.
Yeah.
It remains Boolean. For a considerable number of steps.
Yeah. So
Well, this is why you do experiments.
Yes, I
Okay.
agree. I agree. I mean, so these, I'm not, super convinced that this is signaling something interesting. I mean, it looks interesting. The one that looks super interesting to me is this one, NOR, because it's just two hits in the middle.
Yeah, that's weird.
Like, look at that.
Yeah, that's weird. That's weird.
I mean, I think that is signaling something more interesting because, to be honest, this pattern to me, the ones at the top, feel like, oh, you have a part of the expression. We could always look into in detail and see exactly what it is with these functions
Yes.
I've made.
Yes, we
But
should. Yeah. Yeah.
but um, but like it looks like it's going to be a part of the expression that just gets ignored after the rewrites, and so it makes very many red hits because it's there after rewrites that don't touch it, right? Because
Yes.
my function detects any occurrences, right? It just counts if there are any, and if the count is greater than zero, it just gives red, right?
Sure. I will say, because we know that sometimes it disappears basically almost instantly. So the fact that sometimes these get preserved for, I would say if you have Boolean functions that are preserved for almost the entirety of the evaluation, that is kind of interesting.
Yeah,
However, it would be nice to know what they are. So, I mean, I think the most interesting case is, okay, if there's something in the initial expression that's just preserved, that's one thing. If it's the case that under the rewrites, you're getting other Boolean functions, that would be much more bizarre.
yeah,
Um, and that it must be the case here when it pops up in the middle, you know,
yeah,
I mean, on the one hand, it could just be, borderline coincidental that you have, you know, you have much rewrite happening in this structure.
oh
And if
yeah,
two of them happen to match a Boolean function, it could be significant, or it could just be that it just happens to match it.
yeah. No, I mean, I think that's kind of the intuition that because these, I mean, look at the states in this rewrite. Like, look at the tooltip; it's super long, right?
Yeah, exactly. Right.
So
So the fact that in some of those, two of them in the middle, they happen to, well, it's not that long though.
no, it's
Yeah,
not
that's
that long.
interesting.
So I find this one interesting. Like, okay, let me just get to the end in the evaluations. So obviously, converse, nothing happens in the middle. That would be very strange if we found a
Yeah.
state in the middle.
Yeah.
Like, you see, this is what I mean. Like, we can probably use this as a test case of what I meant, which, it remains Boolean um, until it
Until there's a
until
branch.
there's a branch, and then it's no longer Boolean. It's the same, and it's very similar in all of them. Meaning, what I believe it's happening is that in this expression there is a sub-expression that matches some of the functions, and the
Yeah.
rewrite is not looking at it. It's not touching it.
Right. In XOR, though, it survived the branching too. That's why that example was kind of interesting.
Yeah. Sure. Yeah. Yeah. I agree. Um, anyway, so not converse and okay, NAND. So NAND has this similar pattern
Yeah.
of preserving at first and then branching out,
Yep.
which
Yep.
kind of makes sense to me at this point. Like that the universal one is going to not involve any others in a way. Like, I mean, this is, I don't know, intuitively makes sense to me. But anyway, so okay, so for general expressions, so I have a few comments about general expressions because I didn't really have time to run because these things took some time to just run and find all the hits. So okay, maybe let's talk about general expression at the end, and let's try and figure out what's going on here. So one of the things that we might want to do is figure out obviously which functions are being found, and if Nick is with us,
Nick's here. Apparently, Nick's not feeling
I'm
that
here.
well. You okay, Nick?
I just gonna be off camera today. That's it.
sure.
Are you okay though, Nick?
Yeah, I'm fine. I'm just too sleepy and look terrible. I'm just
Okay.
So
We should have some discussion about scheduling, etc., but do that another time. Yeah. Okay. Keep going, Carlos.
Anyway, so my point is here in this function, because it will be very useful to have this color code, not this one, to have this color code and just be able to glance at the graphs and see the diversity of things that show up. And because I mean, if we see, my bet is that it's going to be mostly just one color all the way, and then it's going to disappear, right? Because it's
Yes, this would be helpful, right?
so for
But
some reason it doesn't work.
It's the exact same thing as
It's
above, but you change the colors, right?
copy paste, just red is changed for these colors. I'm gonna show you why it fails. So let me. Okay, so I hope it doesn't take too long. Okay, in this one, if I do evaluations all motifs rainbow of equal, it's gonna take a few seconds. I hope. Oh no, the ones doing the isomorphism was the one that were taking like 20 minutes or something.
Okay.
Okay, interesting. Oh, this is okay, different color. Okay, this might actually be correct, is it? No, it's not correct. You see that there's some problem here. So you see this graph, wait, let me...
The first few vertices are white?
Yeah, that's a mistake, right? It shouldn't be, because I mean these are all red, and it's just a subset of the red ones that become green in this. So something is
If
going
you're
on.
rewriting the style, if you find some of the motifs, it always takes the last style,
The last style, yeah, that's
the
what I
last one
thought.
that you
That's what I thought.
specify. Yeah.
So how can I amend this?
Or just don't include all of them in a sequence like that. Right? Because your code says you're just making a style, and if you find like motif for and, you have a red color.
Yeah,
If you have like an or, you have a blue color.
right.
But if you have both, you basically, your blue color will override the red.
I see, yes, I see.
Because you just have a list of like a tuple, red, blue. So red is gonna be completely ignored.
But I guess that's fine as long as I get a color in the list, but white is not in the list. I mean, white is only...
What do you mean? White is the first element.
No, yes,
So,
white is here,
so
but...
if everything else fails, besides white, it's gonna be white.
But it shouldn't... I mean, white should only match at the very end, if at all. It's either K at the very end or SK at the very end, and then it's white or black at the very end. I mean, it works fine when everything is red. That's why I don't get it. Like, how is that different? Just that's the only difference between the code, like changing the red for the different color names. How can that make one of the, like, there's some of the vertices
Okay,
here are white.
I'm not following. Let's just pick a vertex.
Yeah.
And what is the problem with one particular vertex?
And look at these two graphs, right? These two graphs supposedly are the outcome of the same function, but one has red in all instances and the other has different color names in the same instances. How is it possible?
I think, yeah.
Yeah.
The main problem is that first kind of cluster, leftmost cluster.
Yeah.
Those should all be colored, as should the first couple of vertices.
Yeah.
But I think Nick's point, Nick, if I understand you correctly, you're saying those in those instances there are several Boolean functions that are being identified, and so it's like how can you pick one color if there are several Boolean functions in those particular states?
No, why are you even sure that this one is white? What other colors you specified there?
White is only for K. So there's no white. There's no white in this list. It's only here at the top.
Oh, maybe it's white blue. It's like on your.
Is it?
It's like you can't really say.
I mean, it looks very white
Oh,
to
I
me.
can't say at least. Maybe you can, but
I mean, this looks exactly as white as the other white stuff. I mean,
well, that's arguable.
no, I mean,
I wouldn't just completely ignore this guy. I think it's just not white. It's one of the colors from your list that is not white.
is it
Well, it's
possible
not.
that?
It's
Yeah.
no. Go ahead.
Is it possible that it's adding the colors?
I don't think it should add it. It should add. You should choose the last one. You can blend them, but I think if you just have a list of colors, it will gonna always gonna choose the last one.
But I
But
mean,
maybe it's just blended by default. You can just test it. Can you just like make a simple experiment, like a graph with a single vertex, and specify a vertex style for it? You two colors.
so let's try. Let's see if my fluency is getting better. So is that right?
Yeah, let's do it with no edges,
Yep.
single vertex.
And then I style it, vertex style.
Yeah.
Okay, so the syntax there is that I have a something like this, right?
Yeah, maybe specify like an actual vertex also, like one arrow, just in case.
Oh,
It's vertex style,
yeah.
then the vertex, and then arrow list.
And then a list.
Yeah, something like that.
Yeah, so
See, no, it's not blending.
the second
But I
thing,
think
yeah.
just try some of the colors from the list. I think it's just something that looks very white.
Well, one thing is you have light gray. You have light gray
Yeah,
at the end
white,
of your
blue,
color
white,
list.
gray. I personally wouldn't.
Oh,
Just...
look at that. Yeah. See,
That's
I would get rid of those light colors
okay.
altogether and just see
Okay.
like
That-
your
On this dark
light
background.
light blue, light gray.
Yeah.
Yeah.
What should I put here? I mean,
You only have so many colors.
I mean, I can do a RGB, I guess.
I'll just pick some one of the cover from the cover data. Some discrete palette or something of colors.
Yeah, but I have to enter it somehow, right? RGB.
Well, it's cover data, and then you just pick a number.
Color.
You can even choose see, it's like the second. Choose color scheme.
Like this.
No, just use those tooltips that the notebook provides you.
Yeah. Ah,
Pick one of the discrete ones, not the gradients.
discrete, like names. Oh,
Indexed, I think. Yeah.
this.
With enough colors for our case.
Yeah. Like
And distinguishable enough. Just pick one of those.
This one.
wow, that one has a pretty light one though, right?
Yeah, but I can clearly see it's white. I mean, I could
What about 27?
27.
Those are all distinct.
But
Oh, there's
28.
distinct on the
very-
white
Oh,
background.
sorry. I went 28.
28. Yeah. Let's try.
Yeah.
And
Then you specify the actual index. So this is like 28 is the scheme, and then another set of brackets specifying an index, and you just specify for each, instead of each color, like red, blue, green, is specified color data 28, 1, then color
Yeah.
data 28,
You
2.
need two brackets. You actually need two brackets in
Two
that case,
brackets?
though.
It's a list?
Yeah.
No, that's the
Really?
it's correct. Just a single set.
Really? Okay.
It's not a list, it's a function.
Oh, it's not a
Structure.
list. Okay.
I'll do something like this. Yeah.
And this is not ideal, but
Or you just do it in a loop then next time.
Okay.
nice. Let's try it. So let's do
You want to do the
reality check.
equals one again?
Okay, some reality check. Okay. Oh, that looks a bit suspicious. Let's try here.
I would have kept that one for
Yeah.
comparison.
Yeah. I agree. Maybe I can cancel now. Yeah, that's what it looked like. Okay, anyway, let me undo. Doesn't work. Something is not working properly, I don't think. Because it's assigning this brown to everything. Well, let's hope my computer doesn't die here. Okay, so this is fine. Let's keep it. Yeah,
Oh, did you choose 23? Kinda looks. The first colors are kinda very similar.
no, I think there's something going wrong. I think because
Okay, what's going on with the rainbow case for equal?
everything is the same color.
Oh,
Which, I mean, it could happen by chance, right? I mean, doesn't mean it doesn't work, but this makes it.
it doesn't work.
What made me suspicious is that it drew. Is that the same color? Oh no, that's not the same color. Okay, no, that's fine. That could be. This could be.
I mean, the real thing to do is to take single way evaluations where you actually use something like the combinator evolution plot, and then you highlight the individual sub expressions, if you will, and you actually take a look at it. Because one problem you're going to encounter no matter what in this setup is that you're giving each vertex one color, and it could be the case that there are 5
Yeah. I mean, this is not the
Boolean functions.
Absolutely. I mean, this is just to have some feeling to begin
Sure,
with.
just to get a kind of a global view of the multi-way system. Yeah.
So what is that? Is that color the same? That's not the same color, is it? No. Okay.
This maybe I shouldn't have suggested 28. Maybe it's too subtle.
Let's just run with this. Let's see what happens because they are different. I think it's working fine.
Not a very colorblind friendly experience. Instead of like coloring them differently, you should have just, I don't know, changing the label, a tooltip,
Yeah.
if some motif found.
Yes.
Yeah. No, I mean,
Yes.
I just think,
Highlighting the tooltips is a good idea, actually.
yeah.
Yeah.
That's
Yeah,
the
that's
other
a good
But-
idea.
Yeah.
many ways to indicate your hits instead of
Yeah.
just coloring them.
Yeah, but this should,
Actually, I would say even having a single color for the vertices, but then including the highlights in the tooltip, it might even be better because it's like, okay, I can see where the hits are, and then I can inspect those hits.
yeah. I mean, so far this is producing something that is non-trivial.
In that last case, well, at least we have two different colors.
It seems no, it's just oh yeah.
It starts
Oh,
as
yeah, yeah.
green.
That's
Yeah.
true. Yeah. Let me just do all of them, see what happens. Because I think it is working now. What is this? No. Oh, this will be interesting.
Oh yeah, let's yeah, let's see what color these ones are.
Oh,
Yeah.
same. Interesting.
Well, those
Yeah.
two have the same, but they're different from the original.
This
Yeah.
this I find the most intriguing, I have to say. Because
I can't. I mean, I like the idea that you kind of recover some Boolean function halfway through, but I'd like to see a case where it's more than just two, where it disappears, then there's kind of a wave, and then it kind of continues to the Boolean emulation continues to kind of disappear and reappear. In this one case, I fear that it's just a coincidence, because for a sufficiently complicated
I mean,
rewrite, these things could appear with some probability. And
but I think-
maybe it's less
Yeah.
probable than I'm presuming.
no, but what I mean, so if we zoom out for a second, I mean, how to say? So these are evaluations of Boolean operators, right? So it means
Yes.
that there's no meaning on the Boolean side of anything that is happening between saying, false and true, right? That gives false. Like there's nothing in between those two steps. So anything that we find that resembles Boolean expressions, we need to disentangle somehow. We need to figure out what's going on, because
Yeah, of course.
but what I mean is that I don't think there's any sense in which we can have an intuition of, oh yeah, there's something that happens and something, I mean,
Yeah, I agree. I agree.
So let me do it for this one.
Just FYI, we maybe have 5 more minutes.
Okay.
So if there's something to be done with general expressions. might be a
Oh
good
yeah.
time.
I need to comment on the general. Yeah. Let me finish this evaluation, and I need to say a couple comments, especially to direct the next few experiments. What happened here? Yeah, they're all very similar in this respect. It looks similar colors. I'm assuming that these are just different hues, and the color scheme is not good. But anyway. Right, so yeah, obviously one of the things that we will do is we'll try to get a better functionality to know exactly what is being hit. By the way, another thing that I should implement, I wanted to know your opinion about this, is I am checking only for the expression of the Boolean operators, right? But I think that what we should check for is the expression with 2 arguments. Because that's, you know what I mean? Like, so the expression and then bracket something.
Yes. Well, I mean, right now we're just looking at true, NAND, false, but like we could have more elaborate Boolean expressions.
No. I'm not referring to more elaborate expressions. Like, I think that there is some phenomena here that it's already interesting enough. I don't think going to more complicated gives us anything in principle, because I mean, we already have some non-trivial phenomena that we don't understand at the level of evaluation. What I'm saying is that we have discovered that in combinator emulation of Boolean evaluations, there is occurrence of Boolean expression emulation expressions, right? So there is occurrence.
Yeah. Yes.
What we have no idea. So I have not checked if these are in emulation syntax, meaning at the very top, I did the introduction not only for the benefit of the viewers, but also for to remind ourselves that the emulation is really strongly dependent on the fact that we have this emulation rule here, emulation syntax, or whatever you want to call it, right? Like,
right? Yeah.
That's what defines the emulation, right? In the combinator side. So I think that we should search for like a pattern that is like this. If I'm searching for and, I should search for something that looks like S. What is that? K, and then something like that. Oops.
So if I understand what you're saying, it's
Right.
that and by itself, you have to give it some arguments, like true or false. If we find and somewhere in the middle of the evaluation, we should also check to see if it's acting on something, such as true or false, or even another operator, like and.
Yeah. So what I mean is,
Right.
what the algorithm searches for right now is this top expression.
Yeah.
I think we should be checking for this expression.
Yeah, I agree.
Okay, good.
Let's see what we find.
That's
Yep.
that's the one question, and then final comment on the general expressions is big exclamation mark that actually emulating the evaluations of general Boolean algebra requires in particular the emulation of all operators of arbitrariety. Like, because, so I was thinking, I mean, we found all the binary operators and we have the expressions for all the binary operators, right? So I guess for the same price, we just find all the arity n Boolean operators and just give the combinator expression for those. And, all the possible Boolean expressions that you could ever write will be in that set, right? So why not just study all the higher arity operators as a group, like we are doing with all the binary operators as a group, right? Like we're extensively covering everything, right?
I see. So just to give an example, if you had like true or false and false or false and false or true, right? That's and actually being given three different arguments in that case.
That was way too long. I lost track. That was way too long. But if you have something like and bracket
Yes.
or, right? So that
Yes.
that takes 3 arguments, right? Because you do something like you do and of P and then you do or of Q and R and you close the bracket, right? So this is some ternary operator on P, Q,
Yeah.
R.
Yeah, right, exactly.
So what I mean is that all the Boolean expressions, they were gonna have some emulation, and we can do it because we have Nick's function that does this, right? We could study all of this in principle with the function I just developed. But my point is, if we already found systematically all the binary Boolean operators in combinator form, why not do the same for example, the ternary ones or the quaternary ones, and have this library of all the possible emulations systematically found, and then we can study those with some criteria that is more experimentally informed, instead of let's throw random expressions and see what happens, right?
Yeah, I agree. Well, for one, I certainly can't tell you, I can't say no when Carlos says let's study higher arity. It's kind of Carlos's thing. But also in this case, it seems necessary. Aha. Well, I was wondering when arity would enter the picture, and
I mean, this was not even my suggestion. This was Nick's suggestion, actually. I mean, it was Nick said last time, and it's written in his function here. I mean,
Yeah.
you need this arity place because you need to know the arity of the thing that you're looking at. I mean, correct me if I'm wrong, Nick, but I think that's what you meant, right? That you need to know what arguments you're taking, and then you're gonna emulate based on that, right?
Oh yeah, for the combinator, it's quite clear. You have to know in advance how many
Exactly.
variables you have to supply it.
Exactly. Yeah, that's what I mean. That's
Yep.
the arity. That number is the arity.
Yeah.
Yeah.
All right. Well, oh gosh, we're somewhat not out of time.
But yeah, this is
Okay,
looking very intriguing.
well, yeah. I mean, so there's some functionality design to be done. So, for instance, highlighting the tooltips is probably a good idea.
Yeah.
Coming up with a better color function is a good idea. I guess starting these searches for these higher arity combinators is another major task. But then there's also the analytic question, if you will, of looking at these. I mean, personally, for actually studying the particular evaluations, I like to actually use something like combinator evaluation plot just to actually see, but trying to understand for these more elaborate ones exactly what is being preserved. Check Carlos's hypothesis. Is it the case that there are just particular functions that are being preserved for some time, and that at some point when they branch, they
Right, I see what you
disappear?
mean. Yes, actually, that should be fairly easy with the function I did last week that highlights. That should be quite easy. So yeah, I'll do that for next time for sure.
Well, cool. I think, I mean, for the purposes of time, I think we might have to wrap up, but we can continue this discussion. We should probably just continue it on Discord so that people can follow it.
Yeah.
And well, this is very exciting. So look, the computational research has really begun, and almost immediately, as one comes to expect when one does these computer experiments, there are strange and unanticipated results. So this is very cool. Thanks, Carlos. Thanks, Nick. Thanks, people, for watching. If you have questions, feel free to pose them on our Discord, and we will, as colleagues, be continuing this on Discord too. All right. Well, this is very cool.
Yeah.
I look forward to seeing this develop. Thanks, everyone, and we'll see you tomorrow for our community forum, and we'll answer any questions that you have then. All right. Cheers.
Absolutely.
Take care, everyone.
Goodbye.
Bye.
Cheers. Bye.